In this video, we are going to be looking at rate laws and reaction orders. So first, rate law is a mathematical expression that describes the relation between the rate of the chemical reaction and the concentration of the reactant. So for a equation, for a general chemical reaction, AA plus BB, and then we're going to form products, because the rate law, it only concerns the reactants, right? If we look at this, it is only caring about the concentration of the reactants, so we don't really care about who the product is, because as we can recall, if we know the rate of the reactants, we can use those to predict the rate of product formation. So in this case, we only care about the rate of the reactants. And this is going to equal to, so the rate law is rate equals to K multiplied by the concentration of A to the X power multiplied by the concentration of B to the Y power. Where we can see that over here, rate is the rate of the reaction. And by definition, its unit is going to be molarity over seconds, right? Concentration over time. K is a proportionality constant, so we also refer it as rate constant. We are going to be looking more into this rate constant later. So this is a rate constant. It depends on the reaction. So it's going to be different for the reaction. So different for each reaction. And then we also have the concentration of A and concentration of B, which is just the concentrations. And then its units is going to be in molarity. And then we have the X and Y. So this X and Y, note that it is not the coefficient. X and Y is a completely different number, and it is called the reaction order. And we're going to talk about what this is later too. So there's no unit to the reaction order. But again, remember, X and Y is not A and B. They're completely different things. So let's first start by looking at the reaction order, which was our X and Y. So it is the effect of the reactant concentration on the reaction rate. So it is going to be determined experimentally. So that's why later on, a lot of examples, you're going to be looking at experimental data, because these are not something that we can just plug it into the equation and know. We have to evaluate the data collected and find this reaction order. So first we're going to introduce four reaction orders: -0, -1, 0, 1, and 2. These are the more common ones. The way how we can express this, so remember previously in our rate law, the way how we wrote this is going to be the concentration of, let's say, A to the -1 power. So mathematically, if we know the concentration, we're going to raise it to the -1st power. And same idea, it's concentration of A to the 0th power, which usually is just 1. And because anything raised to the 0 power is 1. And then the A to the 1st power and A to the 2nd power for each reaction order. Now, the rate of the reaction, what this means is that the rate is directly proportional to inverse of the concentration. So the rate of the reaction is directly proportional to inverse of the concentration for A. And remember that this is 1 over concentration of A. So just in case the -1 is not clicking. And same idea down here. This means that rate is, well, A to the 0th power is 1. So it is independent of A. So this means that the concentration of the of A does not affect the rate. Okay, let me do this again. So it is independent of A. So if it's a zero order, that means that the concentration of this A doesn't really matter. And remember, A over here is a reactant. And if it's 1, that means that the rate is directly proportional to the concentration of A. Same idea, if the rate order is 2, then the rate is directly proportional to concentration of air squared. And just in case, this means directly proportional to. Cool. And then lastly, well, let's think about these rate and how the concentration of the rate and, how the concentration of A and the rate are related in a more realistic term. So this means that if the concentration of A doubles, the rate for a negative first order reaction is going to be halved. So the more A we have, the slower the reaction. And then for a zeroth order reaction, if the concentration of A is added, because the concentration is independent of the rate is not going to be affected. Okay, let me rewrite the heading. So the rate of the reaction, if A doubles, the rate would be halved, unaffected. And then for a first order reaction, if concentration of A is doubled, then because they are directly proportional to each other, they are also going to be doubled. And lastly, if it's second order reaction, if the concentration of A is doubled, then the rate is going to be quadrupled. Okay. Let me just rewrite this whole thing. Okay. That way it's cleaner. So it's going to be halved, no change, doubled, and quadrupled. So that is how the different rate orders of the concentration of one of the reactants can be affected. So if we think about this, well, previously we were talking about the reaction AA plus BB going to become some products. Right now we are exclusively looking at the change in A. So A and B each have its rate order. We're talking about how the change in concentration of A would affect the overall rate based on the different reaction order that A would have. So if it's negative first order, the way how we express it is A to the negative first. The rate will be directly proportional to the inverse of the concentration. And if we double the concentration of A, the reaction rate is going to be halved. For a zeroth order reaction, the way how it's basically independent of A, so sometimes A is not even included in the rate law. And if we double the concentration of A, the overall reaction is not going to change. For a first order reaction, the rate is directly proportional to the concentration. So if we double the concentration of A, then the rate will be doubled as well. And lastly, if we have a rate order of 2 for A, then A is going to be, the square of A is going to be directly proportional to the concentration, the square of A is going to be directly proportional to the rate of the reaction. So when the concentration of A is doubled, the rate is going to go 4 times faster. So when we are looking at the overall reaction order, so let's see. Previously, we had a rate law that looks like this. So rate constant multiplied by A to its rate order, then multiplied by B to its rate order. So this is multiplying before for a equation for a reaction that looks like this. So then this is X is the rate order of A. Y is the rate order of B. So they can both be one be different, both be 1, both be 2. One of them can be 1, the other one can be 2. Doesn't matter. Over here, the overall reaction order is going to be them adding up together. So it's X plus Y. So if A is second order, B is first order, then it's going to be 2 plus 1. The overall reaction order is going to be 3. So that is the rate order. Over here, we're going to look at 2 examples as to looking at the rate order. And again, looking at the reaction order. And again, please try to pause the video and see how far you can go. The rate law for the reaction, as described in the follow, has been determined to be rate equals to K times the concentration of O2 squared times the concentration of H2. What are the orders with respect to each reactant, and what is the overall order of the reaction? So again, this rate is equal to K, which is our rate constant, times the concentration of NO to the power of 2. That means that the rate order with respect to NO is going to be 2. So NO is on second order. For H2, it is on first order because we can see that even if it's omitted, it is to the power of 1. So the overall is going to be 2 plus 1, and that is 3. So it's overall third order reaction. And again, these numbers came from the power in the rate law. An experiment shows that the reaction of nitrogen dioxide with carbon monoxide is as followed. We can see that the reaction is second order for NO2 and 0th order for CO at 100 degrees Celsius. So what is the rate law of the reaction? So when we're looking at the rate law, the way how we write it is the rate equals to K, which is the rate constant, multiplied by NO2. So it's the 2 concentrations of the reactants that determines the rate. So it is going to involve the NO2 and CO. And for NO2, it's second order, so it's going to be to the second power, and it is going to be multiplied by the other reactant, CO. And for CO is 0 powder. So we can see that when something is to the 0th power, it is 1. So that means that we can further rewrite this as the rate equals to K, and then it is only dependent on nitrogen dioxide. So that means that the rate of this reaction is not dependent on the amount of carbon monoxide at all. It is solely dependent on the rate of nitrogen dioxide, which is to its second order. So lastly, we are going to talk about is the rate constant. So the rate constant is specific to each reaction, and its constant can also be determined experimentally. So looking at this, that's focused on the units of the rate constant. So for this unit, I'm hoping that you don't have to rely on looking at the table. You would know how to derive it. So if we have a reaction that is, so again, we're going back to our very classic reaction. It's A and B. Well, if the rate is equal to K, that means that both the concentration of A and concentration of B are to the 0th order, right? Because that way we will have, let me redo this whole thing again. So our rate law will be rate equals to K times the concentration of A to the X times the concentration of B to the Y. So if at the end of the day, our rate is just equal to k, that means that these two multiply with each other to become 1. And that means that x and y are both 0. Because a to the 0th power is 1, b to the 0th power is 1. And 1 multiplied by 1 is 1. So with this said, this means that x equals to y equals to 1. So the overall reaction order for this case is going to be, x equals to y equals to 0. I don't know what I was thinking because it's 0 order. So it's 0, so that's why it's x equals to y equals to 0. So overall, 0 plus 0 is going to have a reaction order of 0. Now, the units for rate is molarity over seconds by definition. So if rate equals to k, then k will have the same unit, molarity over seconds, because they equal to each other. Now let's look at the next case. So for this case, we have rate equals to k times concentration of A. So in this case, this is telling us that in the rate law, this term is going to be 1, right? Because concentration of B is not in there. So that means that concentration of B to the yth is equal to 1 and y equals to 0, because anything to the 0th power is 1. And then A, over here you can see that it doesn't have a power, so it's A to the first power. So in this case, we can see that x equals to 1 and y equals to 0. And the x, y I'm referring to are this x and y. So that means that the overall is going to be 1 plus 0, that's 1. So the overall reaction order is 1. The units, however, so we know that rate is in units of molarity over seconds, is equal to k, which we don't know the units, multiplied by concentration of A, which we know the units because concentration is going to be in molarity. So from here, we can back calculate the units that k should be, right? We can isolate k by dividing both sides by molarity, and then that will give us 1 over seconds. So if the overall reaction order is 1, then the units of k is going to be 1 over seconds. And with the same method, we can determine all the cases. So over here, rate equals to KAB, and in this case, both A and B are to the first power, as you can see, and usually the 1 is omitted, as we know. So x equals to 1, y equals to 1, overall is 2. And we can again look at the units. So these units are going to be different, and when we are looking at the examples or doing the assessments, we just want to make sure that we can have the correct unit if it's asking for the rate constant. So again, rate equals to KAB. The units for rate is molarity over seconds. It's equal to K. We don't know the unit yet, so we're just going to keep it as K. The units for concentration is molarity, and it's 2 molarities because it's concentration of A and B. So to isolate K, we divide both sides by molarity square, right? We divide by molarity, and then we divide again by molarity on both sides. And then we will get 1 over molarity times seconds as its units for K. So if the overall reaction is a second order reaction, then the units of the rate constant will be 1 over molarity times seconds. And lastly, in this case, we can see that x equals to 2 and b equals to 1 based on the rate law that is presented to us. So over here, 1 is 2, 1 is 1. So we know that the overall is going to be 3 because 2 plus 1 is 3. And we can use the exact same way to determine the units of the rate constant. So it's again molarity over seconds. This is equal to K times molarity squared, because in this case concentration is squared, multiplied by molarity over here. So we are basically dividing both sides by m cubed. And on the left side, we are going to get that our units for the rate constant is going to be 1 over m squared times s. So this is how we can derive the units. So again, when we are looking at our problems, don't try to memorize this chart. Try to, Try to derive the units that is appropriate for the rate constant yourself. Because we know that in an equation, the left side and right side has to be identical in numbers and also in units. So with that idea in mind, thank you for watching this video, and I'll see you in another one.